looking good. Let's go live. Hey, we're live. Where's these thingies? Here they are. We're live. Well, what can I say? What a day, what a day, what a day. Welcome to Amber Skies. My name is Blades, it's day 18, and I think we're doing file handling, aren't we? So let's put that up on the board. If I remember rightly, we have to read in text files. So we might just have to do a little bit of file handling. So, I've got my cup of coffee. It's a bit hot though today. So, text files. Let's put you up on the board. And it's going to be for text files. Thank you, telephone, for telling me that I've actually gone online. I don't believe it every time. Without fail. Text files. There we go. How easy is it to read a text file? Well, considering what we're going to be reading, I think it should be alright. We've got .obj files. So that's .obj. I think, yeah. And we have shaders. Because we're doing 3D. Okay. Anything else we might need? For today, not sure, but let's see if we can develop some very, very handy bits and pieces. What we got on TTF? Have we got anything on TTF about this? Colours, surfaces, blah de blah de blah de blah, shut down, shut down, shut down. Oh yes, we've got a solution, haven't we? Let me just get rid of this. Solution to our window problem. It was very easy in the end to get the solution. Quite hysterically. So we'll do that first, I guess. I'll pop you down here, because you don't matter. There we go. Do that. We'll need that later. We'll probably need you as well. There we go. And I can get rid of you. Lovely. Now. Yeah, looks easy enough. Oh yes, and what solution to transparent windows? I'll do that first, because that's where we finished yesterday. It's a very simple solution, one that I thought of late last night, so I implemented it, and let's see the result of the implementation first, I think. Let's have a look, see what we have on code. We have exactly what we had before, except I've taken out is running. That's the only thing I've done. Because I didn't need it for this one. If we test 3D, nothing to be done because I've already compiled it. What does it do? That. Okay, to prove to you that it's working, let's just put you in the center of the screen I know you can't hardly see it, can you? And that's there. And you cannot click on the X button there, but you can on this one here. There's your close button. So yeah, that is 25% opacity. So I can't even bring it down further than that, but I haven't done so because I didn't think it was really worth it for this part of the test. I want to test it with an object on screen to see how it affects the object on screen. So we'll be using this window for testing with. How was it done? Nice, all works. There we go, that's all it was. How was it done? Easy. I cheated. And why not? I'm allowed to. All I did was take the window that I'd done yesterday with SDL2 and then drop in, because I converted a GLFW over to SDL2. So I just dropped in the original GLFW and used that instead. Because GLFW has GLFW window hint, GLFW transparent frame buffer, GL true. And it's one simple command, and it's the same, except it isn't, because the init is different. The init is not called separately, it is done under here, if init. So that's that's just to make sure that GLFW gets terminated properly. Otherwise, there can be problems if you don't do it that way. I know, because I tested it. I've had this one lying around for a while. But now it's just called Window 3D GLFW. So we could actually put that with the GUI into the GUI program. And we can put the SDL2 one into the display program. So we can have two totally separate windowing systems, because it's two totally separate programs. Ironic, but true. It does mean that we might be able to take SDL2 out of there. I've already run a 30-minute memory leak test on the Window 3D, and it came up negative, so I'm happy to use it. There we go. So we're all done there. If anybody wants to have a look at that, it's callbacks, because I do them at the bottom. That just declares me callbacks. You've got your Window 3D, title, width, height, and projection, so you can choose your projection type. Did I not take that out? Yeah, I did, but I've left the thing in, because I'm stupid. Right, okay. That's interesting. Set projection, yeah, I took out the else. So I have cleaned this up a little bit. But as you can see, it's got all the keyboard and also the mouse buttons in it. So we might be able to get the GUI, clean it up and take all the SDL stuff out of it and just use GLFW. And we can use SDL2 for the other stuff. Oh no, we can't, because we need the network. Oh, that's fine. That's fine, then we'll use both. But there is a trick way around that, and I'll show you sometime when we get there. So this is, I'm just going through it slowly, in case anybody wants to have a more in-depth look at it. If you want anything out of here explaining, please let me know. You set up your callbacks here for all your buttons and stuff. The main part is this 122. You've got to set up your user pointer for it, because it's the user pointer that activates the callbacks and lets us gather information, as it were. There's all the callbacks there, and in the header file you've got to be wary to friend them. key callback, mouse callback, and cursor position callback. They need to be friends of the window so that we can get the window information that we need for the callbacks to work. So that's everything there. There's a loads of setters and getters which I've still left in. Well, never mind. Did I leave in the set? No, set title, set width, set height. Yeah, there's no projection rubbish there. I don't know what projection state it's in. End projection. Did I clean that up fully then? I think I did. We do, yeah. Set projection there. Yeah, that's a callback. That's fine, that works beautifully. That's your init. Call set projection there with the width and height. And that does your end projection. That one. And I've left all the hash defines in as well, so you can actually read it properly. So that's that done. Interesting, really. So now we can use if the window hasn't closed. Yeah. It makes your main a bit nicer. Because really all you're doing now is creating main window 3D, setting the background color 0.25 for the transparency instead of 1, which you would normally put. And as long as the window is not closed, or that X button clicked, then we'll carry on clearing the screen and updating within SDLD layer 1. You know about why I put that in, that's okay, and quitting. Lovely. Where does SDL quit come in? Oh yes, it's outside. That's fine. Give that an extra line. Lovely. So, read a text file. Yeah. Let's get on with that, shall we? What we got here? We've got Amber 3D and a struct. Can I take that struct from there to, let's say, here? Obviously not. What? Okay, let's try that again. Struct, Shift, Alt, to here. Thank you. Just tab it out one. That's right there. And then if we go to this one, Shift Alt to that one. Yeah, we'll just take that one in. Lovely. What should we have then? Let's have strings. Let's have strings. What have we got up here so far? Blah, blah, blah. We've got a vector. That's okay. Okay. We'll hash include. Notice where that I'm putting it within the dev area to tell me that I'm doing it for the dev area. So that's important as well. We will need strings. And, oh, hello again. You dingled at me a second time. That's not normal. Who's dingling at me? Ah, bless. And welcome to the stream. Welcome to the stream, whoever's watching. There we go. Switch my phone on, and it says one app updated. Oh, right. 3 new messages. Really? Oh, right, yeah, adverts, great. Thanks. So that's string. We will need a filing, something to do with files, obviously. So we better include fstream. That one. Why is that like that? Interesting. I didn't know that. Oh, it must just be a header file or something. I don't know. Oh, I know why. Yeah, it's alright. Know what I'm doing now. He says. We're going to need a string. So, let's give ourselves a string of strings. To do that, well, we don't know how big the text files are going to be, do we? So what we're going to do is we're going to read them in line by line and fill up a vector. So we can give ourselves a standard vector, I think. That might be a good idea. Standard strings. Now we don't want these hanging around in chip memory on the stack. We will place these out in normal memory on the heap. So string, and we'll just asterisk that, put it out on the heap. Then we are going to read, let's see, a text file. Yeah, that was it. Text file. That sounds good. What will we need to know? Const, standard string. Oh look, I'm using C++ at long last instead of C. No char stars for me. And file. File name it is. There's a reason for it. I'm going to use a file name, or am I going to use a file path? I'll use a file path, because these can be in different places. Just realised. Okay, so that... We're not going to be putting the shaders in the same place as we're going to be having Bob. Bob's in models, if I remember rightly. Yeah, there's Bob. He's here. We better test new folder, and we'll just call this one shaders, so we know that we're going to need them. I'm going to keep these on the top on purpose. So all I have to type in for the file path is model3d / Bob, and for shaders I'll use shaders / shader. So that's going to make my file paths nice and simple, because that's my working directory. As specified, I hope. I hope I specified it. Launch. Yes, we did, here. Working directory, the target is the workspace folder, so the workspace folder is test3d, and yeah, that'll work nicely. So that's how you know what your file paths are. You make it easy for yourself, is the answer. Don't need exec open. Amber's, no thanks. We're dealing with main. Good. This is going to be interesting. Is this all we're going to need? Yes, it is. Yeah, I think I don't really want any other file handlers. So, let's read the text file. Could be very interesting. Right, we have to do a return value, don't we? Because we've got a string to send back. So let's give ourselves a copy of that. So we've got to return something like that. So the first thing we should really do is make one, I think. What do you think? Yeah, we'll make one. And we'll just call it text file. Because we can. So our objective is to... Remember, I'm doing this as a prototype. So this is prototype 1, isn't it? I should really put that here. It's not dev area at all. This is prototype 1. Remember, this is one stage behind now the prototyping for our server stuff. Even though it's going to improve our server stuff remarkably. So we just need to return one. That might be a good idea. Return text file. That's good. That'll work. So already it'll work. Great stuff. And the text file will die there. Yes, it will. What will happen to the strings? They will die. Correct, because that's not an asterisk. Yeah, that doesn't matter. Yeah, that's right. Just looking for me leaks. We'll see on that one. We should really open a stream buffer. We need a memory block. So let's have one of those. Standard. It's in the standard library to do this, and it's if stream. And we'll just have that as our incoming buffer. Okay. Oh, no, not okay. So we're going to need our file path here. We've got and file path, so yeah, okay, we can just put our file path in. Doesn't this give me a hint as to what to do? Yes, it does. Const char star. Okay, that's fine. We've got an ampersand sign on the file path, so it's an address. File path. Why is it char star and I'm using standard IF stream from the C++ library? Excuse me, C++ people who write the standard libraries out there. Could I ask you that question? And if I ever get an answer from you, thanks. Because you won't answer, will you? Yeah, .c string. Thanks. I love doing that. I think that's the best thing we can do. So, what we're doing is we are tying a block of memory called in_buffer to our file so that we can stream in to the buffer from the file. Simple. Nothing complex there. Now, we better test actually that we do have a file. Because if we don't, we could be in a mess. So, if in buffer dot, at least it gives us functionality, is open. That's nice of them. What should we do? We shall do stuff. We shall read a line of text. So char, because it's char star, we'll have a temporary buffer. And we'll make it the size of 255 because that's 256 bytes. Yeah, that's fine. That's just a uint8. So yeah, that's a good size to have. Possibly, are we going to get longer than 255 characters in a line? On a shader we could. That'll be interesting to see if it fails. But it could. There you go. Could fail. Yes, it could. So you might have to increase that to 512, I think. Don't know. Right, let's read this file in. How do you do it? You use a while loop. While in buffer. This is a cheeky, because on Linux and on... Oh, hi, SeppyTW. Hiya, matey. We're doing file reading text files. Let me just bring you up to date. Vector of string pointer. Yeah, I know. Good, innit? It's day 18. We're doing file handling. I've got the solution for the transparent windows already fixed in. We might be going on to OBJs and shaders later if we're lucky. Don't know yet. But a vector string pointer, yeah, why not? To heck with it. It's a prototype. This is in development at prototype stage 1, whereas our main server is on prototype stage 2. So that's already been refactored once. So that's cleaner than this. This is definitely not going to be clean. Already worked with CUDA. Oh, CUDA. Whoa, why would I want to work with CUDA? I've got a server that does it for me. I don't need to work with it. I've got a home server that does it for me. No thanks. I'm not programming CUDA. Yeah, just use a CUDA server and run your program on that. A lot easier. So while in buffer, this is one of the problems with Linux and Windows operating differently. Under Linux, a buffer without any, so still full, can still be considered to be closed because of the way it handles its who can use it, its ownerships in Linux. But in Windows it doesn't. If it's got stuff in it, it's always got stuff in it, and it tells you. Do I often use decal type? What would I use it for? I'm writing an MMO and I'm currently just doing a 3D bit for it. What would a decal type do for me? A decal type would be used if you're doing libs, libraries, DLLs. So, no, because I don't program with DLLs, I program with statics. Oh, I mean, yeah, I've used decal types. Godfathers. Writing, no, once you've written your standard libraries and they're all static, you can close, you can just, I'll show you. Amber 3D is now a static library. If I go down to the profile here, it says static library. All I do is I change that one command and it becomes a DLL. And then I have to go through the files and use decal types, but I do it in a cheap way. And you'll see how that's done later on. There's an easy way of doing decal types, and there's a hard way. But yes, you're quite right. I use static libs, so I don't use decal type whilst I'm programming here. But on completion of a project, yeah, all of these static libs are turned over to full libs, and they are not included in the program. For obvious reasons. For distribution, you would not distribute a static lib unless you're a complete nutter idiot. Or you could compile it all using static libs and then just distribute the programs. Problem there is, if you want to make a change in your program, then you have to update the whole program rather than just a bit of a library. So for distribution, libraries make more sense. It's just what do you feel you need type of thing at any one point in time. And at the moment, statics are fine. So yeah. stages of software development. 1, can't fix this. 2, going panic. 3, questions career. 4, it was just a typo. Cool. Never have that. My stages of software development are 1, prototype. 2, refactor. 3, take a break. 4, fix that silly mistake you made 5 minutes ago when you were refactoring. It's chill, man. It's chill. I have fun. As long as you just got to be careful about certain caveats when working with multi-platforms like I do. And this is one of them, the in-buffer. So instead of to test whether it's still got things in it, and Linux saying, oh, you don't own it, so it's got nothing in it, type of thing, we're just going to type in is not open. Nope, we're not going to use open. No chance. Because there's another one. Underscore. And it's... oh no, it's just dot, isn't it? What I'm talking about. Dot. And we'll just say good. There you go. That gets past all the problems. Oh, come off it. I started on C programming, for God's sake. In fact, I was one of the first C programmers in Britain. That's how old I am. I bought C the year it came out, 15 days after release. Go figure. And I was using it on an Amiga 500. Yeah, that's going back a bit. Ah, those were the days when we had real computers instead of these PC rubbishly put together crappy things. Real computers like an Amiga 500 that worked properly with full bubble memory, no hyperthreading. Yeah, didn't need to hyperthread. It actually had bubble memory, which has never been duplicated since because nobody knows how to do it properly. Or do they? But it's never told anybody. I wonder how much you know about bubble memory. SEPI-TW. Do you know how it works? It's an interesting concept. Go write me some bubble memory. A memory manager that uses bubble memory. And then tell Microsoft to stick it in their ear. Because that's what they killed. Yes. Need to check it. Yeah, go ahead. Yeah, it's called the Amiga 500. Check out how it used memory. It was made by, I think it's made by Commodore. Amiga 500, Commodore, maybe. Same people who made the Commodore 64? Possibly. Can't remember, you know. I think it had that symbol on it. Yeah. Right, so the line I've just typed checks to see if we have reached the end of file. Yes, it does. Inbuffer.good. Never check for end of file. Never check for end of file. Linux will bite you. Right. So, inbuffer. What do we want to do? Let's get a line. Ah, there's one. We'll get a line of text. And we will put it somewhere. Oh, Charstar. Oh, that's handy. We've got one of those. Temporary buffer. Do you need anything else? I think you do, don't you? Yes, you do. You need size. Well, we know the size because we designated it. 255. Oops. 255. Helps if you put numlock on. Yeah, somebody can ever repeat bubble memory. It'd be nice, wouldn't it? Now all we need to do is, sorry, I'm drifting off, fantasizing, text. Text file. This is so simple, this program, it's silly. Push back. what we're pushing back. A string, isn't it? So it's a new, and it's going to be an std string, and it's going to be temp buffer. Yeah, that'll do. Temp buffer. That's it. That puts it in the file. Else. And it's just going to be sdl underscore log. Do we put SD? Yes, we've got SDL here, haven't we? Good. Unable to load file %s, comma, file path. There we go. That's it, really, I think. Was that easy enough? Was that a good start for 10? I can't tell you, Seppi TW. HDD succeeded it? No, it didn't. I'm on Linux. This is Linux. You're looking at it. This is Manjaro, Arch Linux. You can't tell, can you? Ah dear, I love it. Yeah. You don't usually use Krita on Windows, put it that way. I could exit here, couldn't I? But we'd need to return something. We can't return something. Something's gone wrong. Ooh. Oh, we'll crash the system. We'll crash. So I don't want to carry on if we get it wrong. There we go. Because we've got nothing to return. If we've got an else there, we've got no return except that. And that's gonna mess up the program completely and cause segmentation errors anyway. So we may as well do an exit 99. Unix is the right OS. Yes, that's right, it is. Look at C. You can program in Unix, and the programming language is called C. You can do that on any machine. Unix was written in C, by the way. So, yeah, there you go. By, I believe, the American military, of all people. Fancy them getting something right, the Americans. That's good on them. Well done, America. Well done, America. At least you did something right for me. I like that. Even if you did toss all the tea in the harbour and then leave British Empire. We don't mind. We won't hold it against you. Because you gave us C. Do I want to help React OS? Why should I do that? Who is React OS? Why would I want to help them? This is Amber Skies. I work for Amber Skies. And everything I do here is free. My boss allows me to do this and give away stuff for free. Well, yeah, this is a good project as well. This is doing a 3D network that's going to replace internet one day. Is that a good project, do you think? How would you like your internet to be 3D? And why isn't it now? That's what I want to know. Are they making a network that's 3D? at ReactOS? Is their operating system supporting 3D only? Is their desktop going to be 3D? Or is it going to be another one of these 2D Windows crappy things that we've had for the last 25 years? I'm sorry, it's 25 years of Windows. Yeah, I know what they do. But they make Windows, two-dimensional Windows. Like the one you're typing into. So, yeah, why would I help do that when I'm developing 3D? I don't know. Oh, you're on Android. Good on you. Well done. That goes to show the premise of what I'm talking about is great, because my programming language that I use to program in will work on Android. So you'll have 3D Androids as well. And because you said so. All right, okay. Right. I'll ask my boss about that, Seppi. I doubt my boss would be pleased to lose me. Because I'm the only person working on this. And I'm doing it all for free. I give my code for free. I ask for nothing in return. Simples. Let's see, do we need anything else? No, not really. We can now read a text file. Funnily enough, the question here is by Seppi, have you attended Cambridge? It's a personal question and I don't answer personal questions, usually. In this instance, I will answer the question because the answer is no. I declined it. I declined the offer, thanks. For a big reason. A very personal reason at the time, and I think I made a good choice. I'm so much happier. Because I get to do what I want. It's fantastic. I love it. I don't think I want anything else, do I? No, not really. That's it. Text file's read. That's how you do it. Good, eh? So all we need to do now is start working out. Let's see, read a text file, tick. Shaders and OBJ files. That'll read any text file that you give the file path to. What should we start with? Shaders? We could. I don't know, I've never asked one. Do you think the professors have to pay Cambridge for working for Cambridge XD? No idea. Not my realm. My realm is computer design and technology. Sorry. And yes, I do know how the bubble memory was done. And the answer is very cleverly. Oh well. It's a shame it disappeared. I'm still upset about that. I just realised, 40 years on, I'm still upset about it. Oh well. Let's decide what we're going to do next. What we got here? Well, I've just destroyed text files with one thing. Write malware which makes the NSA cry. Gave that up when I was a youngster, sorry mate. And I think half the German group went down at that time. I don't remember if you remember the stories in the paper. But anyway. No, took a chastity vow on my code of non-destructiveness, non-invasive. I think that's a better way of putting it, non-invasive. Right, so we can now read text files. File handling for 3D, text files we can read. We can now read them. And let's see, what should we pick on? Shaders are the easiest. Let's try shaders first. For the testing. I like shaders. Shaders are fun. Should we pick a couple of shaders from somewhere? We'll have to write some now, won't we? Alright, okay. OpenGL 3.3. Okay. Lovely. Oh, that was the worst joke ever. I've just realised that computer programmers make the worst comedians. Well, thank you, SeppyTW. That's awesome. Awesome, mate. Thank you. You've just cheered me up. You've just cheered me up. Just trying to think, what's a good way of going about this? What's this doing here? Ah, right, I want that one there. Okay. Resources. Shaders. Okay. Shader. I will start with a vert and a fragment shader. So let's write a vert and a fragment shader. We can read the text file. So create 4 times shaders. 1 for colored objects, OBJs, and 1 for textures, OBJs. I think we can do that. Why do Java coders wear so big glasses? Because they can't see sharp. Oh, that was Scratch. Oh, I'm putting a message. I'm answering that one. Oh, Scratch. Yeah, fingers down a chalkboard. I had to alter my language there. Can't call it a blackboard anymore, it's not allowed. So, let's create some shaders. So, forget display. Forget Amber 3D. Forget Amber 3D altogether. Okay. Get rid of the main. We're not doing that now. We're doing shaders. Oh, we haven't got any. That's good. New file. Let's call this Amber 3D, isn't it? So let's call it Amber Color. Amber Color. And we'll make this into a vertex shader. Dot vert. There we go. Nothing came up in the bottom right hand corner. Oh my god, what's wrong? It probably will do in a minute or two. If we're going to do a vert, we better do a frag. I'm not going to do any other shaders because, like geometry ones and stuff, because it's a bit overkill for loading in a simple thing. New file, and we'll call this Amber Color frag. Whee! That was easy. What do you think? Amber colour vert, amber colour frag? Yeah, okay. We can do that. Let's see what we've got here. Let's have a look at vertex shaders first. Now, I have to write this in a certain way. So I'm going to use OpenGL 3.3. I've already asked for OpenGL 3.3 in both of the displays. Linksy cat. Oh, that's the whole point of the joke. C# is Java with a colon added. Sorry, a semicolon added at the end of each line. Think about it. Because when C# came out, Java turned around and said to Microsoft, oh, you can't do that, it's just a copy of Java. So Microsoft said, okay, we'll just stick a semicolon in. And that ain't a joke, that's the truth. So we better give it a version. 3.3, we'll just use core, we don't need anything else. We'll start the layout. So shaders have just got a layout and a bit of, well, C at the end, that's all. What we do with the layouts is we have all our incoming information that comes into the program comes through the layout. And there's two types of variables we can pass in. We can pass in variables that vary with each run of the code, and variables that vary for each time an object is generated. A variable that only varies once per face, I'm going to call it object face. I've got to be careful there, because a face is going to comprise of 3 vertices. So the vertices change, but the colour of the face doesn't. So, if you see what I mean. But we're still going to make colour variable, because we can. And we want to do that for shading anyway. Location. Oh, he's got that now, has it? Location. It doesn't give me any telesense help, does it? Okay. We'll start with the first location on the... Does anybody want me to explain this, by the way? About shaders and how to write them? Hope not. Because I will, if you want me to. I'll have that one coming in as a Vec4, please. Yes, I use Vec4s. You want me to explain it? Oh, God. Right, so what we have is a layout system. You don't know what a shader means. Oh, right, shader. Right. Let's go backwards. Clear this lot. Edit. Clear. Right, let's teach you all about shaders. Why not? Just back the U off slightly and let's get something to write on. Let's have a look now. Oh, that's alright, that's comfy. Shaders. Right, there's 10 plus shaders on your graphics card. What they do is, I'll call it a GFX card for short. And they are individual processing units on your graphics card which can be programmed. Programmable, yike. And it uses a language called GLSL. That's the language, which is Graphics Library Shader Language. Yeah. On the graphics card, we are going to choose 2 of these. One of them is called the Vertex Shader. It's got nothing to do with light, by the way. BuffPupP T shame. Vertex shader. I'm teaching about graphics cards today. So when you go out and buy a new graphics card, this is what you want to know about. Your vertex shader, and we are also going to pick on your fragment shader. So these are two processing units on your GPU. Fragment shader. I'll put that underneath. Otherwise it's going to get too long. Okay. There we go. And we'll just do that around the corner there. Right, so you've got your vertex shader, you've got your fragment shader, and that goes to your, for our purposes, it goes to the your monitor. Or TV. Screen. Okay? All the fragment shader does is produce a fragment of the correct colour. So that gives you your colour. I'll spell it the American way. I know. It's because I learned to program the American way. The vertex shader processes each vertex for position. So that gives out position. So what you then do is you come down here and you join together on your monitor. Okay? Like that. Position plus colour equals right place on the monitor screen, right colour. Not every fragment will get to the screen because there is also a depth buffer here somewhere. Okay? The depth buffer decides and filters out anything that you will never see from your point of view in 3D. So whatever your point of view is. So this will have, the vertex shader we will also need to know things like camera position. So these two things here will need to know camera position from where you are looking from, the object itself and its position, what you are looking at, and also light position, where the lighting is coming from. I'm not doing anything that's unlit. I think that's cheap. So you need to know all of these positions in your world. So this is now your world. And you have to be very technical in how you do it. And the way we do it is using something called MVP, which is over here in the shaders, programming model view projection. And that's what we have to, that's what we're coding here. So the shaders here, using model view projection, we are going to write the code for that. And that's what you put in a shader, which then needs to be compiled, linked, and stored upon your GFX card. So your graphics card is going to hold the compiled and linked, oh god, linked, yeah, I think it is linked. Good grief. That pen there. So once we've compiled and linked it, we are going to store that program onto the graphics card. we're also going to store all of the world data for the object here. This object here is also going to be stored on the graphics card as well. So that is on GFX. The camera data we control from the 3D program, and the light we control from the 3D program. Obviously, because they move around. The sun's going to move, the camera's going to move, lights will go on and off. Things like that can get in the way. But the object data will always stay the same. If I've got my avatar, it's always going to stay the same. You could say about animation, not going to detail animation at this point because that really confuses things, but that's the basics of a graphics card and what it holds. It's all about the graphics card, and that's what shaders are. Nothing to do with light, but they do contain the lighting equations, as you will see. So how do we do that? It's rather interesting, really, because it's blooming easy. When confronted with shaders, people and programmers go, "Oh God, you're not doing shaders, are you? They're dead difficult." No, they're not. No, shaders are the simplest programming part that you'll ever do in 3D. It's everything else that's difficult, not the shaders. So what I'm doing at the moment is I'm setting up a page layout of information for our graphics card to store, like a structure, on the graphics card for data to pass through from wherever in our program we're going to be sending it from. Probably a renderer. We'll probably be calling it a renderer or something, a rendering program. So there you go. A simple introduction to shaders and what they do. This will get compiled and placed onto your graphics card. So I better write it correctly or I'm going to knacker your graphics card up, aren't I? Let's take the position. And that is the object's position, I believe. Yes, it is. It's the object's position. Okay. We're happy about that. Let's carry on with our layout. Let's have some more stuff. Location 1, I guess. God, this is hard to do, isn't it? Variables coming in. I'll need a Vec3 XYZ position for all the normals. They are perpendicular to the surface of your triangle. So that means at right angles too. What we can do is we can have a look at where the light source is, and we can measure the angle between the light source and the normal to work out how much light is on that surface. So they're very important, but we only need the XYZ, so we'll have a Vec3. On position we need all 4. Well, we don't, but I'm taking all 4. Oh God, it's C, isn't it? Come on, put your semicolons on. God. Layout. What else should we have? Location. So these are all variables that are very important things that we're going to need. And the last variation that we might have between each triangle for a surface is a Vec4, and it's going to be colour. This is the colour one, isn't it? Yeah, it'll be colour then. I was going to say, if it's not the colour one, we don't want it. Ah, bless. Now, what we can also do is for each face, we can have a set of matrices for our model view projection. Now, this is an awkward thing. It's a subject within its own thing. Model view projection is matrix calculation. So I'll see if I can, I'll put it up on screen first and I'll see if I can explain it. Probably can't, but hey ho, I'll try. You want to form map 4. At least I'm honest. I mean, I'm not brilliant. I'm not a teacher. I'm not qualified as a teacher. I'm just your average Joe who programs. I always put a uniform value as U underscore, just to make sure that I remind myself what they are. Otherwise, I could be in trouble. Uniform. Mat is matrix, so a matrix of 4x4. Do you want me to teach you all about matrices and uniforms? Oh, that could be interesting. That could be a blooming interesting one. How long have I been on for? And have I got any coffee left? I might need it. Good grief. I mean, I'm willing to go through right from the basics of matrices all the way through to four-dimensional matrices and how we come to model view projection from the beginnings to the end. Because it's rather interesting, and I'm actually rather interested in it. I do algebra in my head. I've got one of those horrible brains that does it. So don't worry about it. Well, this one is projection. Projection. So that's that. I'll have another uniform. It's not going to be a mat 4 though. I only want a Vec 3 for this. And this time I just want light position. We'll take you. Right, what we're going to send out. What we can do now is whatever we work out in our program, this is all the incoming data. Yeah, Linksycat. It is that simple. Yes, you've Linksycat just said, so do you just tell the GPU where on the screen it actually shows stuff? Yes. That's exactly correct. We are going to tell in the vertex where the position is, and in the fragment what the colour is. Andrew Droomy, hi there. I want to create a game server for the game King of Kings 3, yeah? Okay. It has closed all over the world. Can you help me with this? Yes, it takes about 10 years. I am not a programmer. I have files of this game. I really want to remember the old days. Go to the manufacturer, send them an email and ask them if they are willing to release the API for the server. If they're not, forget it, if you're not a programmer. If you can find a programming community who are interested, and you advertise on Facebook for a programming community who are interested to build the server for King of Kings 3, and there's enough interest, then people will help you. But first of all, your first step, go to the people who programmed it and ask them for a public API for the server. If you can't get it, then the only way you can build a server is by trial and error. Literally. You try sending a command to the server and see what it does. If it does something, oh good, you found something out. If it does nothing, you don't know. You just tick it off as don't know. And you go through every single kind of normal server type commands you might ever think of, and you've got to try and work it out. That's the only choice you've got, unless you can have the API for the server, which is the application program interface. So ask for that. If they give it you, well done. Tell the community that you've got it. Yeah, or reverse engineer the client. Yeah, that's the trial and error bit. Yeah. So that's how you would do it. The one I'm using for Ultimate Online is now 10 years old and is is very stable, which is why I use it, because it's been done properly and has gone through at least 3 incarnations in those 10 years, from RunUO to SunUO to serve UO, which is now. So 3 communities have contributed to it. But it's that big a project. Around 10 people could get that started off easily. So yes, there you are. That's the truthful answer. Alright, so that's what I want coming in. Now I want to declare what my program is going to issue out and send to the vertex. No, the fragment shader. Gotta get it right. Blades, get it right. So what do we want to send to the fragment shader? Well, we want to send a vec4, which is going to be from the vertex shader, that's us, to the fragment shader, so it's a v underscore. So I know it's coming from the vertex shader. There is 10 plus shaders, you know, you can mess around with. Oh right, decompiling it, yes. But that's a lot of code to wade through, isn't it? Wow. Good luck with that. Not for me. I'd prefer just to write my own server and write my own game and make it styled as King of Kings 3. So, yeah. That's what I'd probably do. It's probably going to take me it'll probably take me 10 years to get this anywhere near King of Kings 3, and yeah, you never know. Colour is what I was going to put there. What else do we need? Andrew Droomy. A friend of mine said that he would provide me with his computer server for the host of the game server. He said asking programmers for help. Maybe they can help. Exactly. Yep. Try Facebook or some social media site and put it up on social media that you are collecting together programmers who want to work on work on recreating the server. But the simplest way is get the API, not Facebook. Oh well, wherever. Whoever is the flavour of the moment. I don't know. I'm not on any of them, so I don't do social media for a very good reason. I'm not interested. I've got enough to do, thanks. Vec3. I will have v underscore surface. Ooh, that's not how you spell surface, is it? Surface. Normal. I'll need that for the lighting. What else will I need? Oh yeah. Right, this is going to really sound weird what I'm going to say next. I'm going to put this in the the vertex shader because of one specific thing. I'm going to show you why in a second. I'm going to add here a calculation, which is the toLight vector, which is, most people say that should be done in the fragment shader because it's to do with the lighting. Nope, not really. And I'll show you why. Out vec3. Right, this is the last one in it. Camera vector v to camera. This is object to light, which I can't spell. Object to light and object to camera vector. Those two vectors give you the angle for light reflection. So now I've done that, what those last two, a lot of people say those are supposed to be in the fragment shader. The answer is no, it isn't. Okay, I said 3 vertices make a triangle. If that triangle covers this whole surface, this triangle here, up on the top right, that has quite a lot of little pixels in it. So that's probably got 100, 200 plus 300 pixels in it. God knows how many. but it only has 3 positional points. So the vertex shader is going to run 3 times, and the fragment shader is going to run for every single pixel that's in there. So if I want to do a calculation, which is going to be fastest, putting in the vertex shader that only runs 3 times, or doing those calculations, well, if you've got a pixel this size of screen, probably 100,000 times. So instead of doing the calculation 100,000 times, we're going to do them 3 times and just send them through to the fragment shader. That will save us an awful lot of calculation time. And that's why people think writing shaders is complicated, because you have to think about who does the calculation, because it's faster to calculate within the vertex shader than it is to calculate within the fragment shader. In other words, lots of lines of code, as few lines of code as possible. So those are the differences between the 2 shaders. Interesting theory. There we go. Is that a semicolon or a colon I put there? Let's try a semicolon. Yeah, that looks better. Right, it's C. Time for some C. Void, main, void again. Yeah, that's C, isn't it? I'm putting that in because you can. You don't have to. You can leave that blank. It doesn't matter. It means exactly the same thing. So let's work out let's start by working out the world position of the model. Where's our model? There's our model. That's our model. That's the matrix that belongs to the model. The matrix contains position, rotation, size, scaling. Position, rotation, and size. Yes, that's roughly about it. There's a couple of other things it's got in there, I think. But that's what's in the matrix. So it's got the position in there. But we now need to put it into the world. So let's work out vec 3. Why vec 3? Let's doesn't make sense. No, let's have vec 4. World position equals, and it's going to be the model, that one. And all we're going to do, matrices are wonderful because all you have to do to combine them is multiply them. So position. There we go. That's it. Right. That's a 4. Positions are 4. Answer is 4. Okay. So we've now got the world position. What else do we need to know? From that, I'm not sure. I'll think about that in a second. The position on the screen is held by a special variable in OpenGL 3.3, and it's called GL position. And that is a very, very special variable name. Okay. Oops, no, it equals GL position. God, my spelling's lousy today, isn't it? Wow. What we're going to do for that is we're going to take the projection. We will multiply that by the view. Underscore view. And we'll multiply that by these last 2 here. We could multiply it by world position, but to make it clear, we'll put U2 in. There you go. That's the actual position that we are going to use on the screen. It is worked out by MVP. Oh, why not MVP the other way around? Why is it backwards? Because all matrix multiplication has to be done backwards. There you go. Rule of thumb. In actual fact, no, it's a hard fact rule. All matrix multiplication has to be done backwards. You can't do it forwards. It doesn't work. So you take your position, you multiply it by the model, you multiply it by the view, and then you multiply it by the projection, and it equals. That's the best way of thinking about it. Never read it left to right. If you see matrices, right to left. Just a handy hint. Bit screwball on the brains, but hey ho. That's the output that we want from the vertex shader, is that one line. All the rest of it is going to now calculate these outputs for the fragment shader. The only reason why we need world position is so that we can work the other bits out. So everything out, well, the next one's going to be easy, I think. V color. Yeah, we'll do you next. V color. Did I use a small c on that? If you use a convention, use it properly. I just chose accidentally to use that halfway through by the looks of it. Equals color. That was easy. Straight pass through. We don't need to do anything to the color whatsoever. The fragment shader will deal with that, so we can pass that straight through. Okay, and now what we need to do is obviously the lighting stuff. Lighting stuff. There you go. Okay, no questions? No, okay. So V surface normal. Let's start at the top there. V underscore surface normal equals. What do we need at the end? A vec3. Why do we need a vec3? Why can't we have a vec4? No idea. Oh, it's a normal, isn't it? We don't want its magnitude, we just want its direction. Okay. Yeah, we'll keep it as a vec3 then. We'll have to open brackets for that. So it's going to be u underscore model. That's the matrix for the model. And all we need to do is multiply that by a vec4, which will be our normals. Yeah, they're a vec3. Normal. I've got to pluralize it. I can't call it normal. It might conflict with an instruction. Plural. Sorry, just thought of that. Because you can normalize. There's an instruction in here called normalizing normals. Or normalize. Never mind. Confusing. Confusing rubbish. Alright, comma. We don't want that part at all. And that's that one done. So just like we got the world position there, we're actually getting the world position normal. And that is equal to the surface normal in the world. So that puts the normal into the world, and we've now got our surface normal. It's simplistic if you think about that's the object that we're talking about, the 3D object we're talking about, and that's the 90 degrees object, the face that we're dealing with right now on that object. So if we multiply those two together, we place it into the world, and then we can now know where in the world we have our surface normal. And that's important. For lighting, obviously. That is surface normal, isn't it? Yeah, right. Let's do V underscore 2. What's the next? Light. 2 light vector equals. And that's going to be the light position, which is u underscore light position, minus, to get a direction. So one position minus the other position equals a vector along that direction. And we will need the world position, won't we, of the model. So that's world position. Yeah. That'll do. Very hard mathematics going on here. So if we know where the model is in the world, and we know where the light is in the world, where the light position is in the world, all we have to do is take the light, minus off the position, and you get a vector pointing from the object to the light. Clever, huh? Clever. And all it is a minus sign. All this is using basic vector and matrix mathematics to work out simple things. I'm not doing anything complicated because it's just confusing as hell. Where's 2 camera gone? There it is. We haven't done that one. 2 camera vector. What will we need for this? First of all, 2 camera vector is a vec3. Why is it a vec3? Because we don't really... It's just a direction. We don't need a magnitude. Right, okay, it's a vec3 then. Now we need an inverse. Okay. Inverse. I think that's a command. U underscore view. No. Put a big V there. VU. Right, okay. That's a vec3. And we're going to multiply that. That doesn't make sense. Yes, it does. Right, the inverse of U view. So that's the view. The view is from camera. That puts it into camera space. So puts your model in front of the camera, or gives you where the model is related to the camera. Does that? That's what that matrix does. So that's your view matrix. It moves the world so that you are looking in the right direction. You actually, as the camera, never move. The world always moves. If you want your head to turn left, you have to move the world to the right. Yes. In 3D OpenGL, it's the only time when the world will actually move around you. It's so eccentric. So we're going to have to inverse the view. That's a bugger. But never mind. We'll just multiply that out. We'll inverse U view. Map4. Yeah, good. Right. So we'll need a vec4 to multiply it by. And well, we want to multiply it by our position. We're at the center of the universe. We're the camera. So 0.0. That's where the camera is. F. Comma. Center of the universe. Never be fooled that the camera moves. Because it doesn't. Even when you move the camera doesn't actually move. The world does. And we have to put 1.0f in there. That last value is called homogeneous position. If you want to know about it, Google homogeneous position. And it'll come up with some really interesting mathematics. And now all we need to do, now we've inverted our camera, because everything is backwards, we just minus the world position off it, don't we? Like before. So it's just the same as one up above, but it just looks stupid. So it's exactly the same as to light vector. To camera vector is we have to inverse the vector because everything's back to front with a camera because we're looking out from the wrong direction. And then we just minus it off to get the world position vector to the camera. So that's what that gives you. Awful, awful, awful piece of mathematics. But that's the answer. Done. I've had enough now. Done them all. Yeah. Have we used all of these? Like, yeah, we have. We've used all of those. Yeah, we have. Have we used all of these? Yeah, we have. That's your vertex shader complete. For every surface, it will run that program 3 times and send those through 3 times. And then the fragment shader will go berserk. All of these outs have to be duplicated on the fragment shader exactly. If you have any spelling mistakes here, it won't work. So copy them. Oh, wait a minute. Yeah, I saved it. Good. So, hash version. This is sometimes where you could get complicated things happening. But most things you can do in here are well documented. So, not really too bad. 1, 2, 3. In. 1, 2, 3. In. 1, 2, 3. In. Ha da 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 da. Lovely. I love programming. It's relaxing, you know. It's therapeutic. That's what I call it. Therapeutic. So, let's get on with our fragment shader. So, we need a couple of uniforms in here. Do we really need them? Am I going to use them? Yes. Yes, I'm going to use them, damn it. Yeah, you can have uniforms coming in here as well, but this will run a lot of times per one uniform coming in. And one set of 3 datas coming in there. There's lots of data coming through here. Uniform comes in once, and it then goes through every single fragment. Oh god, it runs like mad. It's a terrible, well, it doesn't run like mad. There's multiple chips doing it. There's a lot of cores doing this part, I can tell you. So uniform, what do I need? Right, let's have a colour. Colours are vec3s. So we'll have a uniform. I'm going to include it because I think it matters. And it's light colour. Don't have to use it if you don't want to. Some people say that could overcomplicate things. I don't. I say that could be, you can create some really nice effects with it. Especially because when you find out what I'm going to use as a cursor within the game, a mouse pointer in 3D. Has anybody yet worked out how I'm going to design a 3D mouse pointer? I know how to do it. But I'm going to need a light colour, so I'm having it. Yeah. Uniform. Let's have another one. Uniform. Oh god, I can't even spell it now. Oh, we've got a Muppet. Come on, cat. Come on, Muppet. Come on. Jump up. Good boy. Come on, say purry pet. No, you can't stand on that. That's for writing on. It's not for cat paws. Oh, he might even come and give you a purr if you're really lucky people. You coming to give him a purr? You? Come on. Purr at the nice kind people. It's a shame he's on the wrong side of the microphone because that nullifies noise on the other side of the microphone. It's a special microphone. Oh, never mind then. Uniform. Right, what am I doing now? You've made me forget. Let's have a float. Yes, we can have floats. All this matrix stuff. I'll have a shine damper. Why do I want a shine damper? Because without it you can't do water, you can't do metal, and everything just turns to plastic. Uniform. We'll have another float. And we'll have reflectivity, obviously. So we can reflect light. That does help. And did I pull that one over? Yes, I did. Light, colour, shine, damper, reflectivity. We have... Oh, no, I've put it in the main, haven't I? Whoops. I haven't put it in here. Put it in main. Transparency. Are we not picking it up? Doesn't look like we are, does it? Okay, let me put that down as a note. I want those. We'll have to find those from somewhere. Main. So yeah, we'll have to, because we're putting the uniforms in them. We can use this. Lovely things about reading OBJs to try and find us the data, I think. Okay. I'll leave that down there for now as a reminder for me. I think that's a better idea. Get on with the fragment shader. Okay, that's all I need in. There's no other shaders to send things out to, so we're on to void main. Yeah. Next it's the screen. The only thing that's after this is like the depth buffer and the TV screen and stuff like that. Choosing which fragments go on the screen and which fragments don't. Hello Muppet, are you going to sit on me? Oh. There we go. Typical C opener. Right. This is going to get complicated. How? Right. Let's use the Phong lighting method. It's the easiest one going. It's the simplest one going. If you want to look it up, look up OpenGL 3D Phong lighting, Phong, named after Phong, obviously, who introduced this lighting method in C. So what we need is a Vec3. We'll start off here. Vec3 doesn't really matter where we start off with. And it needs a unit. I.e. 1. We need a unit normal. We can't use anything bigger than size 1, otherwise it won't work. So we have to normalize, just in case we haven't done this already, which we should have done, and I probably will have done, v underscore to light vector. No, surface. Surface is first, isn't it? Yeah, surface is first. We'll do that one first. Okay. And we'll do the others as well. Oh, another message. Thingy. Things keep going bring. Hello, messages. What does Twitch want? Andrew Droomy, following me on Twitch. Oh, thank you, Andrew Droomy. Really appreciated, and a shout out to you. thank you. You've made my day. I don't get very many followers. Oh, lovely. That's nice. Unit normals. Unit light vector, okay. Equals normalize. Yeah, we have to do. We don't really have to do this. I just realised we might, if we are better programmers, we won't have to do this. We'll be able to take all of this out of our fragment shader. It'll make it run so much faster because it won't have to normalise 100,000 times every triangle or whatever. So what are we normalising now? What was the next one? Light vector. Okay. There we are. Delete you. Vec3. Yeah. And we'll have a unit. Oh, it's camera vector, isn't it? Yeah. Normalize, and I think that's going to be V T camera. There we go. Lovely. So now we've got all of those down to a magnitude of 1, because vectors have direction and magnitude. It makes all the calculations in the Phong lighting method very, very simple, because when you've got one if you have to divide by this, it'll be size 1. If you want to times by it, it's size 1. So it will have no effect on any of the equation unless you use the direction for what it's meant for, which is measuring angles. Oh, that's all we're using these for. What we're going to do is we're going to take the light, bounce it down to the normal, and then bounce it back to our camera, down our camera vector, and measure the angle between the lot, and use our reflectivity and shine damper to work out how much of this light colour comes back. And that's the surface colour. That's it. So that's how we do all our lighting. It's a very, very simple way of doing it. That's why Phong is nice. Okay, here comes the equation. Let's do the ambient first. That's the easy one, isn't it? So, ambient light. That is the light which is always there. Even when it's dark, if you've got like a TV screen on, it's casting light into the room. If you look away from the TV screen after a minute or two, you can see in that room because there is this ambient light still in the room that is being bounced off all the walls from the TV screen. So you don't. You see, so it's the light, the background light, like background radiation level, background lighting level is your ambient light. It's the light that's always there, even at night. The moonlight bounces around. So that's things to think about there, and we'll have a Vec3 for it because it's just really a light vector, I suppose. So ambient light equals, and what can we call? We'll have a Vec3, open brackets, and I will have I'm going to have a dark red glow. What turn the world red? Might do. Okay. Ambient light can be as low as you like it, but it's got to be there. So we're going to start at 1%, 0.1% for it. That's the highest I ever want to put ambient lighting. I'm going to be tricksy here and put 0.5%. Yeah, 0.5%. For the last one, I'll put 0.25%. That'll just give me a red tint. Nothing more. Bit of a reddish glow sometimes. Because what I'm going to do on the see-through side is use the same gradient of numbers. So this will be supplemented by the see-through window that we're going to be using over the background window. So the background won't be too badly influenced. If we make this like 10%, 5%, and 2.5%, it will just be too heavy a tint on the light. It'll just, well, things will start becoming red, very red glary. Don't like that either. Let's try and work out the diffuse. This is normal light. This is how light normally works. It comes along, it bounces off things, and it scatters around. So diffuse lighting. Not direct light, but diffuse light. Okay, so lighting. So that's non-direct, scattered, normal lighting. The kind of lighting you get in a normal room. Ooh, don't do that. It's not a semicolon. Jeez. It's not command. God, I hate doing these. Let's see where we're up to. Have I got time to finish this? Yes, I've got time to finish this. I'm really an amber colour. God. I want this finished by the end of today. Then I can do the texture one tomorrow. And that'll be easier. Okay, so I need a light intensity, don't I, for this? Float. I'll have a light intensity. Okay. So we've got our ambient light intensity, yeah. Now, I was talking about these being ones. Well, in the dot product, if the magnitudes are 1, the dot product produces the cosine of the angle. So if you ever wonder what a dot product is, in mathematics, that's what it is. If the magnitude is 1, it will produce the cosine of an angle between the vectors. So we are going to dot our unit light vector, that one, with the normal first. So it's going to be unit normal, yeah. Yeah, that's the first one. That's your light intensity. And that's now cosine of theta. Okay, or the angle. So 90 degrees will equal 1. Is that right? No, 90 degrees will equal 0. 0 degrees equals 1. That's correct. Right, that's cosine of theta. There we go. Quickly explained. Produces a cosine of theta. I'm not going to put it in because people really aren't that interested. Yeah, we can do it now. Vec3. We can actually work out Vec3. The diffuse light, because we've got the angle now. Diffuse, shift L-I-G-H-T, equals the light intensity, which is now on the range of 1 to 0, just like these are 1 to 0. Turns out it's a percentage now, because it's cosine of theta, which is a very handy percentage to have. Light intensity, yeah, we'll take U, and we will multiply U by the light colour, I think. Yeah, we'll have it coloured. Normal light, yes. Right, that's you done. Specular reflection, direct light reflecting. So this is your direct reflecting light. Okay, so we need to know, we don't just need to know from the light to the face, which is the surface normal there, to the surface. We don't need to know the direction of the light to the surface. Now we need the angle from the surface to the camera position, because we want to know how much direct reflecting light we see. This will be fun. Right, Vec3. Let's have some reflected light. Oh God, direction. And luckily, because we're in the fragment shader and it's designed to do this kind of thing, it's got a command called reflect, which is actually hard-coded into the chips on your graphics card. Yep, this is hard-coded, folks. That function is there. And we will want minus unit light vector. I want the reverse of the unit light vector, the other direction, and reflected around the unit normal. And that will give it. So that gives us the reflected light direction, which is like, comes down here, reflects off a surface up there, but we might only be looking from here, we might be looking from here. So we're not going to catch all of that reflected light. So now we need to know how much we're going to catch. We've got the direction, so how much of that do we see? So let's add into this a specular factor. To see factor. This is how you get those lovely little lights jingling on and off on the water surfaces when you're looking towards the sun. It gets that nice reflection. So the specular factor. That comes in here. So we're going to dot again to get an angle. We did say float, didn't we? Yeah, dot to get an angle. And we are going to dot the reflected light direction, which we just worked out. Reflected light direction, please. With the camera direction. So that's unit camera vector. There we go. So that's the amount of light that's reflected back over there that actually goes to, so that angle there. We've now got that angle there. Okay, so it's the angle between our eye and that reflected light. Okay, so that's the angles. So that's what we know now. And that's in percentage, which is nice, because it does it for us by the dot product. So now we're going to float. And we're going to work out the damped factor. Because remember, we've got the damper now. So we need to work out, hold on a minute, is that a rough or a smooth surface? No. Yes, is it rough? How much of a rough surface is it? I think it is. So let's have a look at that. Let's have a look at damped factor. That's going, I think it's roughness. I can't remember off the top of my head, but I'm going to work it out later. Because it goes to the power of 2. So we've got to use power, which is, again, a function which is ingrained on your graphics card. We'll take the specular factor, and we will power it by our U underscore damper, which we've passed in here. Shine damper, that's right. Okay, we've got some nice things gathering together here. And what's the next thing we're going to do? Specular light. Vec3. At long last we get to it. Specular. What have I missed? Reflectivity. Have I used reflectivity anywhere? Can't remember now. Where is the reflections? No, I don't use it, do I? Do I really need this? Do I need a reflectivity? Are we using it? Because if we are, we should be using it here. Got it, yeah. We're going to have to put that into the equation for the specular light itself. There's no other way of doing it. Equals, it's a vec3. We've got vex, float, float, and float. So which order do we do these in? I think we have to put the vector first, do we? That's going to there. So that goes through there. Specular goes through there. So now we only need the damp factor. Damped factor is remained in light. So damped factor is the remainder of the light times by how reflective the surface is. Finally, we get to use the last one times the light colour, I guess. Oops, that's not a times. That isn't what's going on here. Shift 8. It just looks a bit high. Okay. You light colour. Yes. Let's add some light colour in here. Let's add some light colour. And there we go. That's it. So that's your Phong. Final lighting. That's your Phong equation, by the way. Final lighting is vec4. Ooh. Vec4. Lighting. L-I-G-H-T-I-N-G. Yay. Lighting equals. This is a fun bit. Vec4. Open brackets. And we have to clamp the values. Clamp. This is another function that's given to us. So, let's clamp everything. Let's see. We clamp specular light. Let's do you first. And we're going to clamp you. God, how does this work now? Comma. Between 0 and 1. Okay. Alrighty. Now we have to add. Because that's just a specular light. So we now have to add. May as well go down to here. Clamp. And now we want diffuse light. Doing them in reverse order. Okay. Between 0 and 1. Can't have them going beyond those two numbers, because if they do, they just mess up your lighting equations and weird things can happen. So we'll add that. And we'll also clamp the final one. Oh, heck. Got a bringy bring. Is it important? Oh, it's Twitch. TickNew is now following on Twitch. Oh, thank you, TickNew. Shout out to you, mate. Thank you very much. You are a star. Oh, this is massive happy days today. I never realised that people were actually interested in what I did, but hey ho, it's obviously you are. That's good. And everything that I do is free. Okay, I'm not going to ask for anything. I know there's buttons on Twitch and on YouTube, Amber Skies at YouTube, for people who wish to support me, but my boss says that I'm supposed to ask, and I say no. I'm giving this free. That's the deal I'm giving. And my boss says, well, you're going to be resulting, on doing this project on handouts, but hey ho. Yeah, I know, I don't care. I'm old enough. I get money off my pensions and things, so I'm happy. Ambient light. Comma 0.0f. I do need a Mac though, I must admit. I want to program on a Mac, and I've never programmed on a Mac, ever. And that will just be... This is a trick of the system now, because it's going to duplicate that 3 times if I just put comma 1. It will turn that into a vec3 of same value, same value, same value, and then comma 1.0f. So that's a little cheeky trick. That's shorthand notation for a vec4. It saves me doing that 3 times and then comma 1.0f. That's all it does. And here we go. Here we go. This is it, folks. The final fragment color is a special value. Very special value. It is GL underscore frag with a capital F, color with a capital C, spelt the American way, equals lighting. This is funny because there's one thing that I've forgotten to use. The surface color, V color, has not been used. Has now. Because it's a surface that we're seeing. So whatever light we see off that surface's color. And that's it. Ain't that crazy, boys? That's the Phong lighting equation on one page. Written in GLSL, which is C. But GLSL is special because where you have like dot, normalize, these are hard coded. These are built in on the graphics card, all of these functions. So what you have to do is, if you want to know more about them, you have to say OpenGL 3.3 GLSL reference manual. Do that on Google and you'll get all the commands that you can use. Clamp's damned useful because it stops this area going above 1, which is the maximum for a light. 1 times the colour is the maximum colour, 100%. So it works out beautifully. And those dots are gorgeous. Used a lot in lighting because of this normalization thingy. But I think I can get rid of those lines there. And where I've used a unit normal, down here, I can just put in V surface normal. Just replace it and get rid of these variables altogether. I can replace them. I hope to achieve that in the future. But for now I'm leaving that block in for completeness, because it is now complete. But 3 normalizations, that's expensive. I wouldn't normally put it in. Normal. I normally wouldn't put normalize in. That's your frag. That's your vertex. Complete. I want an extra space, please, at the end. It's very important. Make sure there's an extra space at the end. And an extra space at the beginning. Same on the frag. Space at the beginning. Extra space at the end. Why is that important? Because we wrote a text reader with inbuffer.good. Think about it. Look it up. So we can read them and we know we get that last line in. So that we know we get line 41 in. Just add an extra line. You'll see me do it on everything. All of my code. You'll see me put those extra lines in. And it's habit, because that's how I read them in. Safety. And it's how compilers read them in as well. They use exactly the same piece of code. So, there you go. Be careful. Are we done there? We've got 2 shaders? Yep. Great stuff. So tomorrow is going to be textures. Wow, that was a biggie. No, I'm not explaining that again. So tomorrow is going to be textures. Yeah, that'll be good. Where's my notes? Texture files. Color shaders complete. Next is, if I don't write it down, I'll forget by tomorrow. Texture shaders. I have an empty brain syndrome. I've had it all my life. And I can't remember things. There you go. Yes, I do. It's weird. It's a weird situation when I'm talking to you about, say, that lot that was on the screen before, about shaders. I can't remember it, but I can talk to you about it as long as I know what I'm talking about. I wasn't talking from notes there. That was all from, I believe, remembering, or what normal people call remembrance. I don't know what I call it. It's just weird. I'll keep my mind blank. It's easy that way. Right. In the meantime, I hope you've actually enjoyed today. I'll keep this on screen there. There's my read text file. So we've got a read text file. We've got our first two read text files to, well, our first two text files to test out, which we will do after I've done the texture shaders. We'll read and show each of these shaders as on screen. That'll be interesting, just to prove that this works. Okie dokies, everything's saved? Nope. As usual. All I can say after that, any last questions before I disappear? Have any coffee left? No, I'm absolutely dehydrating. I am absolutely sweating like a piglet. There we go. Can close you, can close you. Can close you. It didn't even need my SDL today. I've got it open. I thank Linksycat, Andrew, Droomy, and there's other people in chat. SepiTW. Very, very, very big thank you to you all for your chat. You've all basically made me happier today. You've made my day, everybody, and the follows. Brilliant. Thank you. A big thank you. Take care. Keep exploring your code. And above all, have fun.